Welcome to this webinar. To begin with, I would like to invite Dr. Shanta Siri, Head of the International Affairs Division of the National Science Foundation, who is also the covering additional director, to deliver some opening remarks. Over to you, Dr. Shanta Siri.
Thank you, Tilina. Good morning, our distinguished resource person, Dr. Sandeepa, and online participants who are on board from universities, industry, and other institutions. On behalf of the National Science Foundation and the Director General, I extend a warm welcome to highlight some key remarks from the opening. Tilina will highlight credentials and about our distinguished resource person. So I will speak few words on the reasons which were behind organize this kind of a knowledge transfer program. National Science Foundation has taken initiative to develop a digital platform, which is already done, where the purpose is to harness our expatriate, Sri Lankan expatriate professionals who are in abroad, who are in leading industries, universities, sometimes in higher positions like even pro vice chancellor, deans, and industry leading position in cutting edge industries. So our intention was to register all our expatriate with the digital platform and facilitate kind of a cross-border knowledge transfer, some kind of exposure and collaborative R&D and so on, so that our Sri Lankan researchers and other industry and other even students will get the benefit in a way for betterment of the innovation ecosystem. So that's how this knowledge transfer programs also emanated. And Dr. Sandeep also an expatriate who were in the one of the leading universities in South Korea, and he's in a way has done some cutting edge research in the field of electronics. Today, the knowledge transfer webinar more focused on, if you look at the e-flyer, it focuses more on graphene, some 2D materials, and if you focus on last item, that stretchable electronics, as you may see, heard, stretchable electronic is now is the trend, and future will be stretchable electronics will come into play a major role. And of course, if you focus on graphene, graphene in a way post-Moore era, where miniaturization would not give you your expected performance or characteristics in electronic material or the devices. So where you need different approaches, strategies to get your performance, required performance, where thin film transistors and these materials come into equation. So graphene has a leading role. Graphene will be one of the future promising materials. Being maybe expert in the industry and the field, you may be already aware, there are many applications in graphene, optoelectronics, ultrafiltration, and energy storage solutions, and photovoltaic cells. So many applications in one end. From the other end, if you may be already aware, Sri Lanka is blessed with the world's most purest graphite. vein graphite is 98% purity. So the minimal impurity content is found with the Sri Lankan vein graphite, where there are ample opportunities with the graphene, I mean, value addition to our natural resources, mineral resources. So that's why today's knowledge transfer webinar, I mean, program become very important. Our resource person has done ample amount of research and cutting edge research in the field of graphene. So that's why we decided to get his knowledge for the benefit of our research community and of course, academicians and the industry. That's how we decided to come up with this kind of a knowledge transfer webinar. I am sure our distinguished resource person today will deliver his experience, knowledge with his research, I mean, cutting edge research, which will be useful to upgrade your knowledge on the, I mean, current trends and future prospects of the field. Of course, this will be conducted even though mainly in English, but from the beginning, I would say as the presentation or the knowledge transfer proceeds, you will come up with some questions so that you can type it in the chat box. So we will be looking, I mean, vigilant on the chat box, and all the questions will be lined up for the after the our resource person speech. We will line up it for question and Q&A session. Of course, if you have a pragmatic need to raise a question during the discussion point, you can raise hand, and we will, as time permits, we will accommodate some questions. We will try our best. And in fact, after the program, if you come up with some questions, of course, write to us, and I'm sure our resource person will be happy to answer for those questions. That is from my end on opening remarks, and so I'm sure Tilina may be ready to, before I hand over to the resource person. Tilina, over to you, please. You shall highlight our credentials of our resource person. Thank you.
Thank you, Dr. Shantasiri. Yes, let me give a brief overview about our resource person today. Professor Madhumagedon Sandeepa Lakshad Vimalananda had been a research professor of the Advanced IT Convergence Materials Institute of Suncheon National University of South Korea. He received his BSc honors in Materials Engineering from the University of Moratuwa in 2014. In 2019, he obtained his doctorate in engineering, that is printed electronics engineering, at Suncheon National University of South Korea. His dissertation is focused on controlled synthesis of graphene on a textured copper surface. He specialized in synthesis of graphene and other 2D materials, as well as optoelectronics and TFTs. His portfolio contains 10+ Sci-level research articles, 6 patents, out of which 3 are pending, and presentations at 15+ international conferences. Recently, he has also joined as a senior lecturer to the Faculty of Technology of the Uwawelasa University, and having research collaborations with Suncheon National University of South Korea. With that brief overview, I think we can start the main delivery of knowledge by Professor Sandeepa. Over to you, Professor Sandeepa.
Thank you very much.
Yeah, I guess you can share screen. Yeah. Okay.
Yeah. Good morning, everyone. I guess everyone is having a great morning. Today we'll focus on the graphene and 2D materials, especially the application of thin film devices and fabrication of the 2D materials and the thin film devices. I'm Dr. Sandeep Laksha. Let's start our program. So 2D materials, just being 2D materials doesn't give any interest. However, this set of materials provide plenty of potential for the applications, and they show plenty of properties for much more interesting, especially in electronic industry, and sometimes the application in the energy. So one is the most interesting thing is these 2D materials can use to utilize to fabricate ultra thin devices. So 2D materials they are just atomically thin, and the stacking of 2D materials can make the heterostructures. So this heterostructure can maintain extremely low thin profiles simply in nanoscale. Still, these devices can make around 10 nanometer range. So therefore, these materials can provide extremely interesting for the most of the application. Sometimes the flexible devices, sometimes the stretchable devices as well with some kind of engineering. Other thing is the interesting thing is the beyond silicon edge. Now I think we are reaching to the end of the silicon edge because now we are seeing transistors is around 3 nanometer. Go beyond 3 nanometer is got technical and fundamental challenge. So therefore we need to focus on some other materials. So 2D materials also show some kind of promising for this kind of applications. Quantum confinement also some kind of interesting in graphene, and reducing some dimension of these materials can achieve various properties. These materials, graphene and other 2D materials-based devices can fabricate on any substrate. That's been interesting for most of the application like flexible and wearable technology as well. So motivation is somewhat, if you think about the 2D materials-based research, in recent it is continually growing. That means we are not still reached to the maximal level of research. That means still there's plenty of potential for the application and research of 2D materials. That means there's still some level of flexibility to the industry can enter to this field. If you think about the wearable technology, that's one area coming up with the 2D materials with the time and the potential of the future, it is still growing. So that's one of the most motivation for the 2D materials, not only for the high performance electronics, but also some kind of application like wearable technology, also 2D materials can be utilized. That means the research side still it is growing. We have not come to the mature level. And in other hand, there's a higher potential for the applications. Therefore, this will be highly interesting for most of the researchers and the industry as well. If you think about the timeline of the 2D materials, first known the 2D materials invention and received the Nobel Prize. So 2004 invention, so that the mechanical explanation from the use of graphite. So that's the first information about the stability of the 2D materials. That's what I should say. And 2005 TMD, another set of very important material group. That's the semiconductor materials, first invented in 2005. And after that, one of the very important dielectric 2D materials, that's the HBM, also invented in 2008. When we reach 2010, the main hype of the 2D material dominant and the materials also invented. So now we are more focused on the application and some interesting 2D materials we can develop. So that's what the research field is going nowadays. So if you think about the first 2D material-based transistors, that's the 2011 is somewhat interesting year for that one. So here after that, now we have plenty of application we have developed with the 2D materials in the field of transistors like PN junctions, sometimes the sensors, some kind of energy application also. Now we have utilized 2D materials in past period of the conditions. Most of the excitement about 2D materials lies on their potential application, especially graphene. Graphene is some of the very highly stable materials, and we can utilize to develop ultra-thin transistors also. So, on the other hand, one of the dominant semiconductor materials, MOS2, shows some kind of sub-nanometer scale channels. That means the properties of the graphene and this materials shows some kind of very good mobility. That means the switching properties of these transistors also can be achieved extremely high level compared to the silicon edge. So therefore, we have very much excitement towards the 2D materials and the application because of this kind of current trend and current achievements. Today, I would like to cover shortly around 4 topics, especially. First thing is I'd like to talk about the graphene and basic principles and properties and their potential applications. and the introduction to thin film transistors. Especially, I want to focus a little bit on the printed electronics compared to high performance electronics. Why we thinking about printed electronics? That's very important for the wearable and wearable technology and stretchable technology. And some of the few application of 2D heterostructures, and especially why 2D materials are dominating optoelectronics and the potential for the stretchable electronics. If we think about nanomaterials, we can start with the micro-sized particles. These are 3D particles. So one of the interesting materials is the graphite. Graphite simply conduct electricity for one direction, but it's not transparent. If we remove one dimension that we can achieve graphene, graphene is a 2D materials. If we think about graphene, graphene is a highly conductive material. We should say. Other thing is highly transparent. So compared to the graphite, we can achieve completely other properties. So once we reduce one dimension more, we achieve carbon nanotubes, sometimes the carbon nanoribbons. So if we focus on carbon nanoribbons, graphene is a semi-metal. But if you think about the nanoribbon, there are some kind of there's a band gap opening. That means we can use for some kind of transistors as well. If we further reduce one dimension, we achieve the graphene quantum dots. So we get completely different set of properties. Graphene quantum dots are popular for optical excitement. So if you think about the graphene and graphene quantum dots, so graphene is highly transparent, but graphene quantum dots simply respond for light. So we achieve completely different properties. So the nanomaterials are very important. Not only the nanomateria, their dimensions and which dimensions are in nanoregions. Therefore, quantum confinement are very important when we talk about the 2D materials and nanomaterials. First topic, graphene as a promising material. If you think about graphene and their applications are vast variety, but if you think about the electronics application, like optoelectronics, we can use for the LEDs, sometimes the solar cells also we can integrate. Whatever the electronic device that require transparency and conductivity, graphene is a very good option. If there's a band gap, that means semiconductor properties required, we can apply TMDs like materials. Spintronics, some kind of application in memory device. And not only for electronics, some kind of catalyst for hydrogen evolution. Maybe the future energy is a combination of solar cells and hydrogen energy. Therefore, we need to much more reliable catalyst for generate hydrogen for water splitting. Sometimes energy harvesting, as I mentioned earlier, like solar cells and energy storage, especially batteries and supercapacitors, we can currently most of the trends are focusing on that area as well. As a biomedical compatible material as a graphene shows plenty of applications for biomedical applications as well. Therefore, graphene has 2D materials, not just a material that has a plenty of interest for future of the applications. History, when we focus on history of the graphene, in 2004 is the most important year, but before that, graphene has some kind of science. Before 2004, the main problem is people thinking about graphene and 2D materials, they are not stable materials. But 2004 is the first year to understand 2D materials can be stable. So that's the most important thing I think about the history of 2D materials. However, the graphene was first used in 1987, but first we have exfoliated graphene in 2004, but in thin flakes of graphite, especially graphene oxide, was photographed in 1964. So this kind of significant history graphene has, but most important hype started in 2004 with the invention and understanding about stability of this material. What is actually graphene? Graphene is made out of carbon atoms in honeycomb type lattice. So if you think about neighboring carbon atom, it's connected with 3 sp2 hybridized orbits. So this gives extremely high strength for these materials, especially as a 2D materials. So therefore, graphene is the well-known material for most strongest materials in this world. So this is the main reason, more stable and more symmetric sp2 bonds give graphene for their stability. If you think about the remaining electrons, so 5 bonds are the important. This is quite interesting because this is the main reason for the graphene's conductivity. Most of the electrical properties, sometimes we should say optical properties also depend on this 5 bonds. So here's some basic structure of graphene. This is how we understand the atomic scale. Not only graphene, we have some of the other 2D materials as well. One of the interesting material is the MS2. In your left-hand side, you can see the MS2 material. So, if you think about cross-sectional, graphene is just atomically thing. It is less than 1 nanometer, around 1.34. It's rough value. But if you think about the MS2, it is some kind of molecular arrangement of the thin film. But this all these MS2, HP and graphene, they are van der Waals. That means the in between layers, they are very weak bonds. They are van der Waals bonds. So therefore, if you think about other materials also, we can utilize in the potential of the application like graphene. These materials also show the enough stability. MS2, the top and bottom, you can see the yellow color, that's the sulfur atom, middle small blue. This is the basic structure of TMDs. TMDs refers to transition metal dicarbonyls. So this material is good for the semiconductor applications. So in electronic application, we need conductor materials, semiconductor materials, and dielectric materials. One of the most important dielectric materials is the HBN, hexagonal boron nitride. This is one atoms based on the boron and nitrogen. This gives extremely good band gap for the dielectric application, roughly around 6 electron volt. So if you think about the graphenes and other 2D materials, they are aligned. Transition dicalcaneous materials, you can see especially focus on this blue color area and connect with the yellow color set of materials, especially sulfur, selenite, and titanium. So this combination gives very interesting set of materials. These are called TMDs, transition metal dicalcaneous. So their band gap simply lies around 1 to 2 electron volt. That means these materials almost close to our visible range. Therefore, this open plenty of applications. So graphene, we know it's a single metal, it's a zero band gap materials. So, but we can fine tune this materials to open a little bit of band gap, around 0 to, in some cases, close to 1. But most of the situations, 0 to 0.2 kind of band gap, we can slightly open in graphene. And if you think about dielectric, one of the interesting materials is the HBN, as we discussed. Other thing is in hafnium oxide, and hafnium sulfide. Hafnium sulfide is a semiconductor, but hafnium oxide is a dielectric. So convergence of the hafnium sulfide, hafnium oxide is quite interesting molecular. Therefore, hafnium oxide also some kind of interesting 2D materials that we should discuss here, I guess. One diagram. So if you think about the graphene, the electrical properties, we need to convert the structure into wave functions. So that's where we can discuss its electrical properties. I'm not going deep in this area, but electronic structure and band gap, we can equation like this, will convert into billions or so. The electronic structure is somewhat interesting. Before I come to that, I'll give a little bit of introduction to band gap of semiconductor physics. In generally, we understand there's a two band in there, which where the electrons are existing. One thing is the valence. These electrons are the most important for the conduction. The valence electron should participate for the conduction. So how can this happen? How happen this? When the excitement or when we apply voltage, the electrons in valence band should jump into conduction bands. So some kind of should be able to convert into mobile version. However, generally in materials, the valence band is totally filled, and especially in metal kind of materials, the conduction band is empty. That means there's enough space for transfer electron from valence band to conduction band. If you think about the metals, the valence band and conduction band is always tight. That means we don't need to apply voltage. Still, the material has enough electrons, and still some space of the conduction band is available for an electron. So that means these materials act as better conductors. If you think about semiconductors, there's a little gap between conduction band and valence band. There's a small amount of voltage can transfer the electron to the conductive state. That means that's why we observe semiconductor materials useful as a switching method. That means under some certain voltage, there's no conductivity, but another state, there's some kind of conductivity. In the case of dielectric, we observe very high band gap. That means it is hard to transfer electron to this state. Graphene is some of the interesting materials. In the K spaces, this K point, matter is starting to just touch these two valence conduction and valence band, and they are like conical shape in this moment. This is quite unique if we compare to others materials in semiconductor physics. So this kind of conical behavior, just transient behavior, is very interesting thing. So this just this kind of band gaps are generally known for semi-metals. That means that materials can conduct, but still not. Sometimes it is not act as a metals. So this is a very interesting group of materials. So electric conductivity, we can understand with the effective mass. Effective mass is something, nothing is, we are thinking about the conductive, some kind of particles, we modeled with some kind of mass. In most of the materials, they show some parabolic shape, but if we move to the graphene effective mass, and the equation is quite different. It's a short linear equation, and this matrix also show the masses quasi-particles, and therefore the Ballistic transport, that means the electron speed of the electron inside the lattice, generally we can much closer to the speed of the light. It is 0.003 with multiplied by speed of the light. And also we have observed the extremely high mobility in 10 to the power of 5 because of this massless nature of these materials. And other interesting thing is in general materials, electrons won't move much length, but in the case of graphene, the electron in graphene can move very long distance like micrometer scale. That's a very interesting thing. The mobility of this material is very high. Other interesting thing is the density of the state. This gives carrier density of the materials. Unfortunately, if you touch the Fermi level, that means the bands are just touching, the area is 0. That means the density of the state of this material is 0. So that means the carrier density is quite low. That's one of the sometimes advantage, sometimes disadvantage if we think about graphene. I'll come to the advantage and disadvantage of density of graphene later. So, however, therefore, this reason the graphene material shows somewhat higher sheet resistance. In generally, monolayer graphene shows more than 100 ohm per square. So this kind of level. But graphene is conductive, but its carrier density is quite low. That's the basic understanding of the electrical properties of the graphene. Graphene, the conductivity simply means how well material can move the electrons. Actually, in electrons, the movement is simply bred by the scattering. Scattering may be the electron scattering or polar scattering. In the case of monolayer graphene is the best for the conduction. The scattering is lowest with any form of graphene. That's the reason for the better conductivity of the material. If you think about the conductivity, the monolayer graphene is the best option. If you think about other configuration like bilayer or trilayer graphene, so the scattering is somewhat significant, especially for non-electronic scattering. Graphene synthesis. Graphene synthesis is basically two types: bottom-up technique and top-down technique. There are some distinguished advantages and disadvantages. If you think about bottom-up technique, we start with atomized carbon atoms. We can use CVD, chemical vapor diffusion, highly popular technique for synthesis controlled graphene. And other thing is epitaxial growth. It's a very good technique, but if you think about the CVD has much more potential for the applications. What are the advantages of CVD graphene? Actually, they are large area production. We can synthesize graphene in few feet, even if we need it, and better controllability of the crystal properties. We are controlled with the base catalyst materials, but this technique is quite expensive. We need to process very high temperature, like 1000 degrees. We need to maintain extremely clean and clear atmospheric conditions as well. Top-down techniques, we can start with the graphite. We can break down the graphite into thin layers. There's a few techniques. Graphene oxide, one of the popular method, and mechanical exfoliation and solution processing. Also, we can use ultrasonication techniques. We can break down the layer structures because these layers are constructed with the van der Waals bond. Therefore, we can easily break this and separate these layers. This is not limited to this set of top-down techniques, are not limited to graphene, but also some of the other 2D materials like HDL and PMDs also we can use top-down techniques as well. CVD techniques also we can use for TMDs like materials, but the mechanism will be a little bit different. But the main there's a plenty of advantages. One of the keys are high throughput production. That's good for the industry, and somewhat economical technique. We don't use high temperatures in this kind of situation. So therefore, the energy is the one primary issue in thinking about this kind of materials. But whatever the crystal properties we had from graphite, we will get for these materials. That's why we can't control the crystal properties. Only thing we can do is that we can degrade the crystal properties, but we can't improve the crystal properties. That's one of the disadvantage. And the lateral size is limited to few micron. In the case of graphene, we can reach up to full size display like few feet, but in this case, it's limited to microscale particles. If I give the introduction to CVD graphene, this is one of the most interesting technique today world. So CVD techniques, we use CH4, sometimes C2H2. These gases, we let it to atomize very high temperature, like 1000 degrees. And we use substrate. Generally, we use copper, sometimes nickel. Nickel is good for multi-layer graphene. Copper is very good as a substrate for catalyst substrate for single-layer graphene. And we let nucleate. And this carbon and this catalyst surface has a one important function. It absorbs materials, and after that, the absorbed material will diffuse to the nuclei. Then that's how the nucleation and growth mechanism in CVD technique. But in some situation, we use very low pressures. That kind of techniques we call low pressure CVD. Other thing is the atmospheric pressure conditions. But if you think about high quality graphene, the low pressure CVD is the much better option. So if you think about the CVD graphene, we can control number of layers quite easily. We can limit the number of layers to one single layer by using CVD technique. That's the one of the best advantages we have from the CVD. Other things are we can produce any large amount. So graphene, if you think about graphene, CVD is one of the dominant field for high performance electronics. So there's still plenty of problems remaining with the graphene synthesis, especially focus on CVD graphene. One thing is the rapid. We need to synthesize graphene rapidly. You will understand why we need to synthesize graphene rapidly. Because if we integrate to some other process like printed electrodes, also they have potential to integrate this technique. Therefore, we need to synthesize graphene, and we need to control the synthesis, especially in the aspect of properties, some kind of crystal qualities, and the grow number of layers sometimes. Graphene should be able to grow in some certain area. These are the two of the very good key areas we need to focus on the potential problems in graphene. If you think about graphene synthesis, now we have two approaches actually. First thing is the lower attachment barriers. That means even the graphene was nuclide, it takes quite some time to grow. That means there's a high energy gap should reach this carbon atoms to add to the graphene nuclei to grow. So one of the foreign element like oxygen, now we have understand, can significantly reduce the edge attachment barrier. This gives very high potential for the rapid synthesis. So within the scale of seconds, we can synthesize continuous film of graphene using this understanding. Other thing is the concept is the increase in number of nuclei. That means if you think about surface, if you increase the number of nuclei, we can continuously fill the surface quite quickly. This is one of my research paper I took it from. Actually, we have a textured surface to increase the surface range of some kind of points. And after that, we apply rapid input of the CH4 gas. Within 50 seconds, we have also completely covered surface. Therefore, these two concepts are now currently mostly implemented for the concept of the rapid synthesis. If you need high quality graphene, maybe the option is the best option to lower the attachment barrier and go for the continuous film of graphene. Control synthesis, one of the other understanding is the we need to grow graphene in some certain application, some circuit only in selected area. So there's basically two concepts. One thing is a seeded growth. Other thing is the controlled growth of graphene in only in the selected area like bilayer, monolayer graphene patterns. So seeded growth, here we are applying very high surface free energy catalyst we can implant on the catalyst surface. During the CVD graphene, due to this high surface energy, nucleation will only happen in this area, and graphene will continue to grow this area through around this point. This is the seeded growth mechanism. Other concept is the control synthesis. Control synthesis is somewhat we can control the surface texture in different points. We can control the surface free energy and nucleation properties. for monolayer and bilayer graphene, for some kind of nucleation control. So we have introduced this technique, actually texturing surface, some kind of contamination, suppress the nucleation, therefore high amount of carbon can adsorb this area. This carbon ability to go bilayer graphene. That's the basic concept of this kind of technique. Other thing is, if you lower the technique, the texture surface diffusion is highly suppressed. Therefore, we won't achieve any kind of electrical conductivity if we texture the catalytic surface. But if we maintain is very smooth, we start observe even at low temperature conductivity. So this kind of concept now being implemented to synthesize graphene only in selected area with selected pattern. Therefore, in the aspect of graphene, now we have mostly addressed the most of the situation, graphene and selective growth. And still the quality also can be very much control the crystal size. Therefore, application now it is almost graphene is ready for some certain application, but still plenty of things to improve for the future applications. If you think about the top-down technique, graphene oxide is one of the techniques. We simply oxidize the graphene materials. So we can oxidize this using sulfuric acid as potassium permanganate. So this is one popular technique currently used in graphene oxide. I guess this is one of the popular technique because some know about this one. Graphene oxide is actually not conductive. This is almost like dielectric, some certain applications, but we can reduce the graphene oxide by just applying heat around more than 140 degrees Celsius. We can simply degrade it, some chemical methods also. Then we can achieve reduced graphene oxide. Reduced graphene oxides are not better as the conductivity, but still plenty of application remain. Other techniques like mechanical exfoliation and electrochemical exfoliation. Electrochemical exfoliation, what we are doing is inside the graphite structure, we are trying to create some kind of little air bubbles and push the layers apart. So this is one of the key area in electrochemical exfoliation. This one also gives very high throughput exfoliation technique and gives, unlike the graphene oxide, this gives quite good graphene because there's no oxidation. Sometimes there's a potential for oxidation, but oxidation can be neglected in this technique. Other thing is mechanical exfoliation. Unlike the first graphene peel-off technique, now we can use ball mill kind of techniques for mechanical exfoliation. So this one also gives a possibility of the very large amount, but the crystal size is quite low in this technique. That's the one of the negative feedback of the mechanical exfoliation. Not only this one, the ultrasonic based exfoliation techniques also currently available. Characterization of the graphene, especially when we focus on the industrial friendly techniques. One of the most significant thing is the Raman spectrum. Other thing is the FSM, optical microscopy, especially probe techniques like AFM are very interesting because wafer scale now we can use probe techniques to analyze probe techniques. Are now so many instruments are developed for wafer scale analysis. Therefore, one of the interesting factors is the FM and other probe techniques can be directly utilized for industrial application, wafer scale analysis. This is very important to understand some kind of damage area, some kind of the thickness of the materials. We can understand some kind of electrical properties and how the electrical properties are changing. We can understand if the probe technique. The main graphene signature is the Raman spectrum. In Raman, signals are highly sensitive. Defectiveness is one of the most interesting factor we can understand. It's a D peak, the first peak close to 1,350. D peak we can observe. This is higher the D peak. Generally, we observe materials have very high amount of defects. So one of the key areas in electronic industry, we are trying to reduce the defectiveness of the materials. So therefore, the Raman and this kind of probe methods are good for the academics as well as the industry. Here are a couple of interesting applications beyond the electronics, I would say. One thing is the water distillation and water purification. Interesting, there's a set of researchers found the graphene nanopore structure. So they can distill or separate iron from the water faster than our current reverse osmosis technique. It is almost hundreds times rapidly we can clean the water by using this technique. One of the other problem is once the water and oil contaminates, it's very hard to separate. most of the time we are using mechanical remedies like taking out the water. But graphene also showed this kind of potential application because graphene is highly hydrophobic but still oilophilic. That means graphene materials can absorb oil and they don't absorb water. Therefore, we can use this material to separate oil and water. Once the water is contaminated with oil, still the graphene materials is quite interesting material for this one because we can see we have a synthesized graphene form and this performance is quite high and absorption capacity is almost more than 100 times compared to the oil absorption capacity in graphene. This is quite interesting area of the graphene as well. Some of the other applications are energy. Hydrogen evolution reaction also we use and water splitting. Currently, we are using platinum and carbon, but platinum is still a metal. With the time, it can lower the performance, but graphene, it's chemical stability and some kind of physical stability we can run for long run. But there's still one little bit of disadvantage. That means for activation, we need to apply a little more amount of energy. But doping techniques now we have implemented. Sometimes the combination of MOS2 kind of materials, 2D materials also, we have implemented for the catalytic materials. In batteries, as we know, graphene is highly conductive materials and layered structures means there's enough space for ions to move. That means therefore graphene-based batteries show some kind of fast charging and high capacity. So it is almost like supercapacitor plus batteries. But unfortunately, graphene is not a supercapacitor. Supercapacitor is another set of field. But graphene-based applications showed very good performance compared to the conventional batteries. Other thing is perovskite solar cells. Currently, perovskite solar cells are something like we are most known for the PSS. It is a conductive polymer. We are used for perovskite sources, but 2D materials like MS2 and WS2 have showed some kind of work function close to this material. Therefore, 2D materials also now can be being used for this perovskite solar cells. That means that we can achieve very longer lifespan for this material compared to the currently used polymeric materials. And the performance also quite high in these 2D materials. So now we focus on the electronic application. One of the interesting is the thin film and thin film transistors. Thin films are nothing, just the materials synthesized in extremely low profiles. Thin films structures are made of the layered structures. The thickness of the one of the structures is sub-nanometer to a few micrometers. In traditional materials in thin film industry, it's go to the micro scale, but now the current understanding of 2D materials, we are simply reaching to the sub-nanometer scale. Therefore, thin film industry also, therefore, materials are then devices are much thin means we can easily flex, we can develop flexible devices. Application of the thin film devices simply due to some of the interesting properties of the thin films, especially graphene and other 2D materials. One of the interesting is the ultra thin devices. As I mentioned, we can simply synthesize the thin film device with the graphene in sub-nanometer level. And other thing is these are flexible. Graphene is very strong. MOS2 also showed enough strength for flexible application and transparency because these are highly thin. Not only the materials, device also can synthesize in highly transparent. This is good for the application. Even in the we can synthesize transparent displays as well due to this kind of reason. So potential of the application of thin film transistor are quite high. Displays, wearable devices, energy as we discussed, even biomedical applications and sensors also, we can utilize thin film devices. Transistors, especially if you think about graphene-based transistors, graphene and other 2D material-based transistors, they are field effect transistors. In the case of field effect transistors, transistor characteristics simply controlled by electric field. So graphene and other 2D material-based thin film transistor also one of the category of field effect transistors. So field effect transistors and developed with the thin film devices simply called the thin film transistors. And we have used thin film coating technique, like sometimes coating, sometimes physical vapor deposition, sometimes chemical vapor deposition. So these are the primary techniques we are used to develop thin film devices. Thin film technology is simply, I would like to categorize in two ways. One thing is the high performance electronics. High performance electronics, we are more focused on performance, like processors. We need to achieve maximum switching capability. And how fast can we switch this one? Therefore, we need to use different set of instruments. One thing is the layout by layer deposition technique, physical vapor deposition techniques, and chemical vapor deposition techniques. We are highly implemented for this technique. And lithography and plasma etching techniques we can use for the designing devices. And other interesting is the printed electronics. Printed electronics is highly focused on the economical fabrication and how to synthesize more economical electronic devices. High throughput and economical device designing and the wearable devices are most focused on printed electronics. So here we are using traditional printing techniques to synthesize graphene-based devices. Instrument used for fabrication of this technique simply simply use the electron beam evaporation and magnetic sputtering. These are the thin film transistors basic instrument, but unfortunately graphene and other 2D materials, we can't use this one because even we use graphene, we need to deposit some metal contacts. But using electron beam and magnetic sputtering, it won't work because electrons, beams, and plasma simply damage the 2D materials. Therefore, we cannot use this technique, but still we have plenty of options. That means thermal evaporation, because 2D materials are highly stable under even some certain temperature. Therefore, we can use thermal evaporation techniques and the atomic layer deposition for deposit some kind of contact. Otherwise, we have to change the architecture of the thin film devices. CVD and PVCD, we can use to directly deposit 2D materials on this kind of substrate. Lithography and light-etching techniques still we can use to design 2D material-based device. That means the present techniques still we can use for our device design. That's a very good aspect for the industry and modern research. Printed electronics, I would say it's focused on the high throughput production. So first interesting thing is the rod technique. That means the one single line we can apply whole device design. That means one set of station we can print dielectric materials. In this station we can print semiconductor materials. Other thing is contact. This set of printing process we can implement to one single set of process. This technique is simply called rod-to-rod technique. So rod-to-rod technique is highly popular in printed electronics. That means one single process we can print whole device. So that's where we can achieve printed electronics in more economical and high throughput production line. In printing techniques, even the rod-to-rod is a basic concept of the total production line. We have plenty of printing techniques. These are all the currently existing printing techniques. The advantage of printed electronics is we can implement these printing techniques to modern application like electronics. One of the two, I would say Gravia and Offset are the most popular in printed electronics. Gravia can deliver very sharp devices. So, but the device scale is quite high, micrometer. That's why it is quite hard to sometimes retrieve for high performance electronics. But since some ink displays, still we can use printed electronics, especially for wearable technology. We can use this technique to print electronic device on any surface, like our clothes, gloves, whatever the wearable device. That's one of the other key factor about printer electronics. If we think about wearable technology, we have to simply understand the printer electronics. So Gravia, I'll give a brief understanding about the Gravia and Offset. So Gravia is some kind of cylinder. We have glued some parts, and these screws can simply transfer the ink, whatever the 2D materials based ink, to our circuit area. That means our polymeric layer. Generally, we use that kind of materials we can use for flexible devices. PDMS is some of the popular materials for stretchable electronics. So we can use gravure technique. Simply, there's a set of groups. Groups can simply transfer the pattern to the other substrate. In offset printing, we use some kind of stamping kind of technique. So a stamp can carry the recording and it can transfer the substrate. So these are the two basic techniques most we are highlighted when we're thinking about printed electronics. 2D materials can be used for printed electronics, especially. We are more focused on the solution process technique. For printing, we need physical particles in very small scale. So that's what happened in solution-based technique. So we can exfoliate these small particles, 2D materials from bulk form, and we can prepare ink as necessary. We can connect most of the binders, what are the materials compatible with these 2D materials, then we can simply print. So this is one of the example of the printed electronics. Hafnium sulfide, first we can deposit, after then oxidize, then we can have dielectric hafnium oxide. Almost one of the dielectric materials, graphene can be used as a conductive material. So these materials we can print by using printed electronics. So, but however, the one of the drawback of this printed electronics, we cannot, because here we are dealing with the most of the time polymers, sometimes 2D materials. Polymers are the most interesting to printed electronics, but the compared to the polymer 2D material shows very long life and durability. Therefore, 2D materials got more attraction in printed electronics in current world. Otherwise, people are more focused on the polymeric materials. However, the electric properties, actually the transistors based on 2D materials and printed electronics can achieve around 10 to the power 6. In silicon edge, we are thinking about 10 to the power 8. That's the minimum standard we are looking for. But still some certain applications like sensors, still we have a manageable level of on-off current by using this technique. So most of the printed materials, and depending on the quality, we can achieve 4 to 6 of the on-off ratio by using printed electronics. Okay, how about CVD graphene? Can we connect with the printed electronics? That's one of the interesting factors, because printed electronics, we are not only focused on printed, sometimes we can integration of the other process, also the printed circuits. Actually, CVD technique, CVD is very important because we can synthesize extremely large area of graphene with highly controlled and very controlled and manner. So therefore, this kind of materials we can directly utilize for device fabrication. So actually, this kind of longer sheets of graphene we can currently can be synthesized using CVD technique. So the main thing is this kind of film, if we can implement transfer during the printing process as a sub process, so we can simply influence CVD graphene as one of the key materials for printed electronics. This will give some kind of sight of the very good achieving and improving some performance of the printed devices. If you think about thin film transistors, there's a multiple architectures, but we have to focus on our process. If you think about printed electronics, we can achieve with many architecture. But high performance electronics, because of some limitation, we have to limit and control our electronic gate design process. Okay, Howard, can we synthesize thin film transistors only made of the graphene? Answer is yes. Actually, we have graphene. Graphene is conductive materials. And if you think about graphene nanoribbons or quantum confined the graphene ribbons, they show some kind of opening of the band gap. How about the graphene oxide? Graphene oxide shows some kind of dielectric properties. Combination of these three, we can achieve graphene transistors. However, there's a on-off ratio is quite low in these devices. It's around 1, but this is still good for some kind of application like sensor. This is one of the interesting fact about graphene. Graphene is a semi-metal, but still we can find into device fabrication. But if we fully focus on graphene, we need to open the band gap. Therefore, multiple way opening band gap. One of the interesting thing is quantum confinement, especially we find in graphene nanoribbons. And doping also very interesting area. Other thing is bilayer structure, integrating of some kind of semiconductor materials, something like MOS2. So this we can achieve this kind of techniques to dope and some kind of open some kind of band gap for some certain application. So let's focus on the how much performance we can achieve by using this technique. One of the most interesting thing is the quantum confinement. We can achieve nanoribbons. We can open band gap up to more than 1 electron volt. But problem is if we reach this kind of limit, the mobility gets very low. That's the one drawback of the graphene nanoribbon. But still, this material shows some kind of potential the application of thin film devices. Other thing is the doping. Nitrogen doping also showed extremely good band gap opening. And actually, the thing is that we can alter the electrical properties with the control the electric field. That's where this doping techniques are very important. By using phosphorus, that's one of the interesting doping material in graphene. Actually, we can achieve up to 1 electron volt. But all of these techniques are actually good for the some certain level of application. Some kind of processes, still graphene is not good enough materials because we cannot achieve very high band gap and we cannot achieve high on-off ratio. That's one of the drawback of the graphene if you think about the high performance electronics. But still some certain application like sensors, graphene is still a very good material. Optoelectronics. Optoelectronics is almost dealing with the materials and light. So materials and light interaction and bring it to some certain application. Simply we call optoelectronics. One of the interesting application of 2D materials is also other than TFTs, thin film transistors. We more focus on processors and electronic switching and some certain application like sensors. And optoelectronics, we can bring it to some kind of real devices like its displays and some kind of photodetectors. During this presentation, I would like to more focus on LED and how the transparency of the graphene and graphene materials should more focus on the high performance electronics. One of the interesting thing, as I mentioned, graphene is highly transparent. So even in our laboratory scale, we can synthesize graphene transparent more than 97%. And electrical conductivity in the effect of the sheet resistors roughly around 140. The main question is why graphene is so transparent. One thing is the graphene is highly thin. That's the one reason for transparency of this material. But other thing is the low carrier density. The carrier density low means a less amount of scattering points. So even the theories now being developed that high the carrier density material is starting to lower the optical transparency. So graphene materials has a very low carrier density, as I mentioned earlier. Therefore, graphene, that's why graphene is highly transparent. So if we need to improve the graphene conductivity, what we need to do is improve the carrier density. So, but still, as you know, conductivity is almost proportional to mobility and carrier density. Mobility of the graphene is quite high. We can achieve at least 10 to the power 5. So this is the limitation. Therefore, that means the amount of number of carrier density improvement is we don't want to go for extremely high level. Therefore, still we can maintain high transparency even with the quite high electrical conductivity. That's the most interesting thing about graphene as a transparent conductive electrodes. Let's focus on the application of the graphene and required amount of sheet resistance. In most of the applications like LEDs, displays, we need quite low sheet resistance. So that means single layer of graphene still we can't use. We need to go for multi-layer graphene. So multi-layer graphene simply shows the low sheet resistance, but sometimes its mobility is sacrificed. But it's still good for most of the applications. And some certain applications still we can use single layer graphene without doping. And other way hand, we have to use some kind of doping technique and some kind of device architecture to improve the electrical properties and lower the sheet resistance of the materials for the practical applications in optoelectronics. Graphene has transparent electrodes and some certain applications. We can improve in few techniques. One thing is we lower the defectiveness. High the defectiveness of the graphene materials, they scatter. That means electrical properties are low. Therefore, we can focus on the high quality materials in this. That's the one area. Other thing is the introduction of the other nanomaterials as a total, like silver nanowires. Silver nanowires we can implement, and still we can change the architecture of the silver nanowire focus, and still we can achieve extremely high conductivity and very few saturation of the transparency, even with the doping techniques. Other thing is the work function engineering. So we can work function in between graphene and based devices. So this work function gives very good advantage for eliminating drawbacks of the graphene materials. Therefore, graphene materials and work functioning also one of the very currently dominant focus on the how can we bring graphene materials to modern applications. So that's the main focus on work function engineering for graphene-based devices. So graphene and other 2D materials, can we synthesize fully 2D materials optical devices like LEDs? Answer is yes, but almost to show some kind of emission of the light. But unfortunately, the optical efficiency is cut low in this material. If the research in early stage, maybe we will have fully 2D displays, fully 2D material space optical device in the future, because still the efficiency is around less than 1%. But the engineering and some novel understanding of the materials are required to bring it to practical applications. Heterostructures. Heterostructures is some kind of a building, something like a building blocks of the devices. So we can use different bandgap 2D materials and in a layered structure manner. So this structure simply provide should have different bandgap, should have different quality to achieve some of the different applications, different advantages. In some certain situation, heterostructures showed much better mobility compared to the single set of materials like MOS2. The application of the heterostructures are not limited to one single area. It's most of the areas like light emitting devices, solar cells, and transistors, and most of the application there's a plenty of potential of heterostructures. Device performance simply depend on the materials quality and how can we engineer these materials. So there's a plenty of architecture of heterostructures, but one of the simplest form is single heterostructure. That means combination of two set of materials, MOS2 and tungsten disulfide. So this kind of two different materials, two different band gap, we can achieve different properties. So this is the basic understanding about the basic devices of the heterostructures. 2D heterostructures, we can assemble them in two different types, especially mechanical assembly and simply self and epitaxial growth. Mechanical assembly is sometimes drawback in the application, some certain application, because mechanically exfoliated materials are quite low, and it is hard to align the crystal structure, and we cannot achieve sometimes the atomic scale resolution. Therefore, mechanically exfoliated technique is not the best option when we focus on industrial application, but still it is good enough for the application of the fundamental studies. If you more focus on the industrial application, we need to more focus on the self growth or direct growth of the heterostructure. That means as example, tungsten disulfide growth on molybdenum disulfide. So this kind of situation gives very good advantages, something like a crystal alignment, that means atomic alignment, and we can control the whole device performance. Compared to the mechanical devices, the direct growth devices show extremely high performance. One of the advantages of this direct growth techniques are they are quite highly photoactive, and so even in the application like transistors, this material shows extremely good performance. So now we are talking about high performance electronics. High performance electronics, so we need to achieve maximum amount of performance. By using these 2D materials, heterostructures, we can achieve atomic scale resolution. That means very good contact. Very good contact means we can achieve very good electrical properties as well. The pinning of the electrons, that means the if the electrons are not well attached, the electron transfer is quite low. There's a huge barrier. But fortunately, this direct synthesis technique almost give insight of the achievability of the high performance electronics. Like a transistors, we almost can be achieved almost close to the 10 to the power 6 on-off ratio. That means the on-off ratio is almost like 6 to 8. Still, we can achieve very high on-off ratio compared to printed electronics, because in printed electronics, achieve very well stacking is not possible, but in this kind of application, we can achieve for high performance electronics. In other hand, we can device architecture, we can use vertical heterostructure and lateral heterostructures. Vertical heterostructures are somewhat easy fabrication process, but lateral heterostructures we can only synthesize by direct dot techniques. As example, first we need to go MS2. After that, laterally we can synthesize WS2 from here after that. So there's some kind of synthesis difficulty in lateral structure, but still this kind of lateral structure shows better performance than vertical heterostructure. But if you think about the fabrication possibility and simplicity, vertical heterostructures got much more attraction. Okay, I'll now focus on the beyond high performance electronics to some kind of stretchable electronics. Stretchable electronics is more focused on the wearable technology. We need to wear as a glove, sometimes a cloth. We can synthesize some kind of sensors we can integrate to our gloves. Sometimes we can integrate to our cloths. So even under stretch condition, these devices should fully function. So this is the basic concept of the stretchable electronics. So one of the key challenges in stretchable electronics is how to prepare the conductive lines. That's the most of the research are now being focused. And flexible devices we can synthesize, but extremely stretchable electronics, most of the time we are preparing flexible devices and integrate some stretchable electronics, stretchable electrode for devices. That's how most of the stretchable electronics is now being focused. In stretchable electronics, stretchable electrode design was focused on stretchable designs and graphene's kind of materials we are being used for this kind of material, especially 2D materials. If we imagine about the nanoparticles as a conductive materials, in most of the electronics, still we can use metallic nanoparticles and they can sinter. But in stretchable application, there should be some room for the stretching. But nanoparticle will not work for stretchable electronics. Therefore, only 2D materials like this kind of architecture work for the stretchable electronics. That's why 2D materials are highly interested in stretchable electronics. There's plenty of architecture now being used for printer electronics and printer electronic device design. One of the things is the simply change the architecture. Other thing is the pre-strain substrate. Sometimes we can control the graphene wrinkles. Graphene wrinkles also, and we can transfer into the required substrate. These are the basic concepts now we are being used. Even the graphene has some kind of interesting properties. Compared to other materials, graphene has negative thermal expansion. Due to this negative thermal expansion, graphene can be used to synthesize wrinkled graphene in atomic scale resolution. So this kind of all these concepts are now being implemented for the application of stretchable electronics. So I have given just a brief introduction to the stretchable electronics. And as a conclusion, if you think about 2D materials, we can use for high performance electronics and even for the practical application like wearable technology and some kind of printer electronics. Printer electronics and wearable technology may be the future of the wearable technology, but still plenty of issues we need to address. We need to know how to synthesize, how to control the properties of these 2D materials. So how can I bring it to practical applications? And thing is, still the research are being developed. We have plenty of opportunity for the future of the good applications. Thank you very much for your attention.
Thank you, Dr. Sandeepa. And I think excellent content delivery and with attractive images to give the message, I mean, very efficiently. And we highly appreciate your explanatory content delivery. And I think I'm sure participants got more knowledge on areas and synthesis and applications from R&D to application. Of course, you made an excellent justice to the topic proposed in our knowledge transfer program. Of course, I know at the moment, large-scale remote, I mean, in rural villages where water supply and drainage board is not feasible to supply water, some companies or non-government organizations are bringing some reverse osmosis plants to the rural community for potable water supply. But after some times, many of those become idling or not usable with the, I mean, not repairable. So those are, of course, turnkey type imported solutions. But today I learned that graphene has, I mean, high potential for water purification. I mean, faster than, I mean, as I am layman, not
Yes.
expert in electronics, but as I understood from your presentation, graphene has potential for higher performance compared to, I mean, existing reverse osmosis plants. So you not only gave the new knowledge, but of course, I presume our Sri Lankan researchers to you shed light on some new research areas, but of course, which could be demand-driven, addressing the societal needs. One example is the water purification application of graphene. So that highlights our graphene not only value-added products aimed at export industry or for global market, but of course, some applications giving solution to our societal problems. Graphene has that potential. So I was vigilant on the chat box, but there were no questions typed. But so now we open the floor for Q&A session. Anyone who, I mean, want to ask the questions may type in the chat box, or you could raise hand so that we can take the questions. While maybe audience may be getting ready for questions, I want to ask one question from Dr. Sandeep. Maybe with the based on today's
Yes.
program, maybe one university, Sri Lankan universities or industry, they may be interested in connecting with you, maybe for supervising research projects or conducting collaborative research projects. If there is any such kind of a need, I know you are very somewhat committed and very pressing commitments. But if there is such kind of an interest in times to come, how your schedule will be? Are you in a position to give you, collaborative kind of arm to the researchers? How you are positioned?
Yes, actually, I'm quite interested for some kind of collaboration, especially in Sri Lanka. we are popular for some kind of graphite. So therefore, most of the universities in Sri Lanka also, they are more focused on the graphene-based research also. Actually, I would like to share my knowledge and I would like to collaborate with them in any situation. So I'm fully open for some kind of collaboration with Sri Lankan universities.
Right. Okay, thank you. Because as you highlighted, many universities and of course, like Sri Lanka Institute of Nanotechnology also has done some kind of, I know many are engaged with the research in the area of graphene. Therefore, based on today's your program, we will be publishing a concise, very concise note with our website. Therefore, it will have a spillover effect where who visit our website will look at the opportunities, and that's why I was asking that question. And with this, as I understood, graphene, maybe there are some good physical and chemical, maybe electrical properties. So when from R&D to go for real application, let's say, as a layman, what I have heard, production process out of getting graphene out of graphite, somewhat challenging. Of course, laboratory level may be okay, but scale up level and when you go for commercial level, consistency with quality expected output parameters somewhat challenging. So with your experience, how you could see, to mitigate or overcome the challenges and to the application side?
Yes, so that's one of the problem in graphene, because graphene is a 2D material that's being it is highly sensitive for the environment. So graphene is stable materials. There's no problem with that one. If you think about these capacitors and sometimes the battery kind of application, we need very consistent and extremely high quality materials. But during most of the production, some kind of contaminants can add. For the capacitors, especially some kind of silicon particles, silicon nanoparticles, they can connect. So these are very drastically reduce the properties of this kind of applications. So if you think about the chemical process, so still we can achieve consistent performance, but like a CVD kind of graphene, we need to highly control the environment. So even bring our graphite material to practical applications, I think still we have plenty of opportunities with controllable manner, because a mechanical exfoliation may not be the answer, but still we can go with some kind of application of the solution process techniques. So these are the most of the time we are thinking about the highly pure form of materials. So that's the one area we need to focus on, even the research also, because how to control the impurities, not about the graphite, but during each step the controllability of the purity is very important. Some certain applications I have mentioned, capacitors, that's one of the major drawback. We cannot achieve sometimes the highest level of capacitance with theoretical value, but actually the impurities are adding during the process. Therefore, we need to more focus on the research on how to synthesize in more purest form. We don't want to add any kind of impurities. So that's one of the key and very interesting area. Even we think about the research. So that's it, more focus. Still, that doesn't mean said we cannot do. So actually, we can do, but we need more research. Some kind of situations.
Yeah, right. Thank you. And maybe I am asking more questions, but maybe for it common to, that's why from application side, for the graphene applications in energy storage solutions, of course, one potential area. I know there are some ongoing research within our Sri Lankan context,
Yes.
some flow type energy storage with once the solar and renewable sector now growing, definitely future will be demand will be for energy low cost energy storage solutions. So I know for water purification and maybe high supercapacity application, there may be requirement for a more pure and 100% pure material. But for energy storage solutions, of course, as a layman, may need not such kind of a highest purified level. But what is your, how you see graphene in energy storage applications, and
Yes.
is there Sri Lanka, if any industry or research team think of developing and really applying side of not only from benchtop level, but
Yes.
if any research team focusing on really one kind of a application oriented graphene based research or applied research, at the end of the day trying to give energy. Of course it should be now, we have to remember that parallelly researchers are developing other materials as well for energy storage. There is a competition in the global level, so your economies of scale and cost effectiveness and affordability and efficiency will be the your unique value proposition. So how you see Sri Lankan graphite or graphene, whether we would be able to win, kind of lead get a competitive advantage in future?
Yeah, that's actually a very interesting area. So if you think about energy storage, we need to focus on batteries and supercapacitors. Actually, I'm not an expert, but I have some idea about graphene. So the graphene is simply used in the anodes in batteries. So that's one of the popular and most research area in graphene batteries, as I know. People have tried different set of graphene, but even in the natural graphite and synthetic graphite. So there's a little difference in natural graphite and synthetic graphite. Synthetic graphite is one of the advantages. We can control everything. We can have extremely high quality. But reality is in the currently people are more focused on synthetic graphite. Even the synthetic graphite is very expensive. Natural graphite we can have somewhat lower cost, but synthetic graphite in some certain application, especially sometimes the batteries, it gives sometimes better performance, even the lithium ion diffusion. But that doesn't mean these natural graphites are useless. But in some certain situation, if you need a more economical way, if you need to implement, so compared to other traditional battery materials, still the graphite gives extremely good performance. So if you need to achieve maximum, still people are quite interested in synthetic graphite also. Even the heat transfer and most of the properties currently research a little bit better than natural graphite. So as being said, Sri Lankan graphite is highly pure and best quality graphite. Even there's some market for economical production of batteries and everything. So that's where I think Sri Lankan graphene will dominate, because if the industry required, Sri Lanka is the best place to buy the natural graphite. So it doesn't mean the Sri Lankan graphite cannot target with the high performance electronics and high performance batteries, but in some certain situation, we have very good hope. And one more thing, I think we need to more focus on Sri Lankan with Sri Lankan graphite. We need to achieve closer performance with the natural synthetic graphite. So we should find and more research the area where how to improve the crystal quality of the graphite close to some kind of synthetic graphite. So that's one area I should suggest. Another thing is still, it doesn't mean Sri Lankan graphite are bad. Sri Lankan graphite is the best we have, and it's natural, plenty of application. If you think about the application with the natural graphite, so Sri Lankan graphite will dominate there. There's no doubt about that. But I suggest it's still plenty of room for Sri Lankan graphite to develop. We need to compete with not other graphite. We need to compete with the synthetic graphite. That's my suggestion.
Yeah, thank you. So I will stop asking questions. There are many, but we will give opportunity to audience. From the audience, any questions, please? There are no raised hands. So anyone can. Yeah. Madhava, anyone from the audience, if they want, they can unmute their mic and they can ask the question. Eh?
Of course, they can unmute themselves and ask questions.
Yeah. Participants, if you have any question, you can unmute your mic and ask your question, please.
I'm from the Open University. So
Yes.
from the electronic department,
Yes.
many students are doing research for the research project electronics field, but most of them are doing with the microcontrollers and so many things like those things.
Yes.
And they don't have funds actually. They cannot spend actually at least even 1 lakh. That is a huge amount. And
Yes.
also they would have knowledge about these graphene things and like those things. Can we have some research level explanation or something, and how can we get the funds and knowledge about those things?
Okay, I think in the case of Hanla, that's one of the problem in Sri Lankan researchers, most of the researchers facing. So if they want to go for some kind of some certain level of high tech and advanced level research, they need more funding because most of the research techniques and techniques and materials they are quite expensive. My suggestion is we need to. I think we have two options. One thing is a collaboration where the resources are available. Other thing is the so sometimes the funding also can be allocated with the if we connect with the foreign universities. So especially for some kind of collaboration. So if we are going to collaborate with foreign universities, we need to bring some knowledge and some kind of facilities with us. That's true. But still we have some kind of room for the collaboration, I guess. That's where we can have some kind of resources as needed. Other thing is we need to apply for fundings. Maybe even it is not available in Sri Lanka, there's some kind of fundings available in foreign fundings also. They can be applicable. In my suggestion is the knowledge in the knowledge wise, the collaboration is the best thing. It's easy, we can easily achieve that task. Even the resources also, collaboration also a very good sign. And collaboration is one key point I'm thinking about. Other thing is we need to apply for foreign fundings. That's where we can generate more funding, I guess. Even in our my position also, the funding is one of the biggest challenges because even in some certain situations, some techniques we cannot do because the limitation of funding. So some of them are very expensive. That's true. So even in Sri Lanka, this is the problem of one of the area. My suggestion is try to collaborate with even in Sri Lankan universities. Then we can find some kind of resources like analytical techniques, analytical instrument, even foreign universities, maybe we can allocate some funding for us. Also, that would be my suggestion.
Yeah, Dr. Sandeep, I also can complement what you exactly
Yeah.
highlighted for that addressing the question. As you highlighted, I also strongly believe that collaboration will sometimes null and void. I mean, money. I mean, if
Yeah.
you get lucky to join with a foreign collaborative partner with a state-of-the-art university's excellence center, definitely there will be opportunity to access to material, consumable, as well as high-end
Yes.
R&D equipment, your knowledge. With regard to the knowledge, of course, knowledge is now on board. I am sure, as Dr. Sandeep, from my first question, Dr. Sandeep already highlighted, he is willing to, furtherance his knowledge and experience. Definitely, with regard to graphene, his ample amount of expertise and research experience definitely will help Open University team. So I think we can, with consent of our Dr. Sandeep, we can link you with maybe Dr. Sandeep in your free time. I know Dr.
Yes.
Prasad Senadira is from Open University. We are already in contact with him, Dr. Prasad from Open University, and we can, with your convenient time, we can have a kind of a, brief discussion to how could you, facilitate in a formal way to the Open University research team. And also funding, regard to funding, National Science Foundation also has, kind of research funding, but with the economic, this prevailing turbulent circumstances, funding, giving grants, bit kept in abeyance for the moment, but hope 2024, we hope we will receive some capital funding, which could be divert more focusful manner if research teams are get together with joint partner with the industry, and without not the blue sky research, but demand driven, particular addressing a particular industry or societal problem, by at the end of the day targeting kind of application, field level application, of course, with making a convincing case and justifiable case, may be in a position to, secure some kind of funding. I cannot give 100% guarantee, but as per our mandate, one of key mandate is the research funding. So that is why I am sure we can link Dr. Sandeep with the Open University research team through your International Relations Director, Dr. Prasad. Please be in touch with Dr. Prasad, and we will later on, we will make the, of course, as Dr. Sandeep maybe having too many commitment, but he may be in a position to allocate a time period for a brief discussion to initiate the dialogue. Yeah, thank you. Any questions? I think there are no more questions. We can conclude the session. To conclude the session, on behalf of the National Science Foundation, I extend our sincere appreciation and thanks to our distinguished resource person, Dr. Sandeep. It was, I mean, very, very useful session today. Our objective 100% achieved. So as someone can interpret low participation, but 30, I observed throughout from the beginning to the end, almost 30 was there that indicate their interest, and the today session, I mean, participants have connected who actually have the need. So therefore, I am sure there will be more. If you have any question when you go to your work again, and if you come up with some ideas or collaborative research ideas, maybe suggestions, you can write to us. You can, Tilina, if you could write our email address in the chat box, it may be very useful.
Yes, Dr. Shansiri. And and just add a point, if Mr. Neil Fernando, Neil Herath, if he could also post his email address, it would be useful for future communications. Yeah, we will.
Yeah. So if you have any further questions, write to us and we can make the link and catalyzing and mobilizing role. And today gave a very exciting, I mean, highlights in the field of electronics. And I know with the limited time, you made a good job. Within 1 hour time, I am sure you have more than 10 to 15 years research experience cannot be shared within one hour time, but you made an excellent job. So thank you very much. And as rates in the, I mean, discuss in the Q&A session, we will be contacting you to link you with the Open University, please.
Yeah,
And
sure.
for dear participants, now the webinar recording is now available. It is link is shared in the chat box. Please share it with give the message to your colleague researchers, and my email is now written in the chat box, and you can write to us, and we are more than happy to, I mean, propel and furtherance of today only the knowledge sharing session, but this will be the initial starting point, but with ended up with collaborative research or partnership furtherance of the same. So we will do our best to propel that kind of endeavors. So thank you very much, Dr. Sandeep. And
Thank you very much for having me.
Yeah. So before wind up, do you have any final concluding? I mean, yeah. Oh, Dr. Sandeep.
Yeah, actually today session was quite interesting because we were able to introduce the talk about graphene and 2D materials with Sri Lankan researchers, I guess. So the Sri Lanka will be in a very good position to touch graphene-based application because we have a source of the graphite. This is one of the best what we have. I think the future of the graphene and 2D materials will be more focused on the one side is high performance electronics, other side is wearable technology. Especially if you think about the graphite, I think we need to more focus on energy like batteries and wearable technology. That's where I think. If we think about high performance, maybe the that graphite will not be the opportunity, but future we are seeing very good demand for the wearable technology and energy. So I think Sri Lanka will have a better future if we more focus on more research on that field. But anyway, we need to bring Sri Lanka graphite to the next level. We need to compete with some kind of synthetic materials and high performance materials. That's where I'm saying Sri Lanka should move on.
That's the key message. And yeah, thank you very much. And we will again, we will meet maybe with the Open University team. And thank you very much for your
Thank you very much.
knowledge sharing and your valuable knowledge. And thanks a lot. Have a nice day.
Thank you.
Okay. Bye.
Thank you.
Yeah.